Hello dear students, welcome to mathematics class. In this class, let us discuss one more theorem on subgroup. So the statement of this theorem is the intersection of two subgroups is also a subgroup. So it means that if there are two subgroups H1 and H2, then the statement given implies that H1 intersection H2 is also a subgroup of G. So therefore, here already they have given H1 and H2 are the two subgroups of G. Let us prove this one. Let H1 and H2 be the subgroups of G. So if H1 and H2 are the subgroups of G, then we have proved one theorem, that is here. Let H be a non-empty subset of a group G, then H is a subgroup of G if and only if AB inverse belongs to H for all A comma B belongs to H. So here, if this condition satisfied, then H is a subgroup, and if H is a subgroup and this condition must hold in that H. So therefore, here they have given that H1 and H2 are the two subgroups of G. Then therefore, for all A comma B belongs to H1, it implies that AB inverse belongs to H1, because by using that statement of that theorem, if H is a subgroup, then AB inverse belongs to H, or if AB inverse belongs to H, then H is a subgroup. That we have already proved. So by using that theorem, here we have written that for all A comma B belongs to H1, it implies that AB inverse belongs to H1, and consider this as the first expression. Then since H2 is also a subgroup of G, therefore for all A comma B belongs to H2, it implies that AB inverse belongs to H2. So it is also by using the same theorem, that is for all AB belongs to H, it implies AB inverse belongs to H if H is a subgroup. So here H2 is a subgroup, then we can use the result as for all AB belongs to H2, it implies AB inverse belongs to H2, and this one is the second expression. And now we know that A belongs to H1 and A belongs to H2, right? Because here in H1 there is the element A, in H2 also we have A. So it implies we can write this as A belongs to H1 intersection H2, because that A is the common element for both the subgroups. And then B belongs to H1 and B belongs to H2, it implies that B belongs to H1 intersection H2. Then, so here we have A in intersection of two subgroups and B also in the intersection of two subgroups. So therefore, we can write that A comma B belongs to H1 intersection H2, right? And from 1 and 2, from the expressions 1 and 2, here in 1 we have AB inverse belongs to H1 AB inverse belongs to H2, right? So therefore from 192 we can write AB inverse belongs to H1 and AB inverse belongs to H2. It implies AB inverse belongs to H1 intersection H2, right? So therefore now A and B are the elements of H1 intersection H2 and AB inverse is also the element of H1 intersection H2. So therefore we can write the conclusion as for all A comma B belongs to H1 intersection H2, it implies that AB inverse belongs to H1 intersection H2. So therefore H1 intersection H2 is a subgroup of G. So hence the proof. So here we have proved that if H1 and H2 are the two different subgroups of G, then their intersection is also a subgroup of the same group G. So it is about the intersection of two subgroups. But for the binary operation, union of the two subgroups, we cannot definitely tell that whether it is a subgroup of G or not the subgroup of G. So let us consider one example that the union of two subgroups may or may not be a subgroup. So right. So now let us consider that as the note. The union of two subgroups may or may not a subgroup. The union of two subgroups, it may a subgroup of G or may not a subgroup of G. So now to satisfy these two statements, let us consider one example. Now let G is equal to 0, 1, 2, 3, 4, 5 be a group under the binary operation addition modulo 6. Now consider H1 is equal to 0, 3 and H2 equal to 0, 2, 4. H1 equal to 0, 3 and H2 equal to 0, 2, 4. Now let us verify whether these two are the subgroups of G or not. Now first consider H1. So here the binary operation is addition modulo 6 and these are the elements 0, 3 and here also 0, 3. We need to write the table for addition modulo 6. Now 0 plus 0 is equal to 0, 0 plus 3 is 3 and 3 plus 0 that is 3, 3 plus 3 is 6 and if we divide that 6 by 6 we are getting the remainder as 0. So therefore here these four elements are the result of the addition modulo 6 table. So here all the elements of this table belongs to the given set. So therefore closure law satisfied, right? And here since G is a group, it follows the associative property. In these elements we have 0 and 3 also, means for the elements 0 and 3 associative property holds good since G is a group. So therefore associative property also satisfied. Then next one, identity law. So here this one is the topmost row and the first row is same as the topmost row and the corresponding element is 0. So 0 is the identity element. So hence identity law also satisfied. Then we need to move towards the inverse. Now inverse of 0. So here 0 is there here in the first row, the corresponding elements are 0 and 0, means inverse of 0 is 0 itself. And similarly for 3, here it is 0, the corresponding element is 3, and here also it is 3, inverse of 3 is 3. Hence all the 4 laws satisfied for H1, so therefore H1 is a subgroup of G, right? Because already it is a group by using those 4 laws. If it is a group, then it is the subgroup. And similarly for the second one, H2, that is 0, 2, 4, 0, 2, 4. Now 0 plus 0, 0, 0 plus 2, 2, 0 plus 4, 4, and 2 plus 0, 2, 2 plus 2, 4, 2 plus 4, 6. If we divide that by 6, 0 is the remainder. And 4 plus 0, that is 4, 4 plus 2, 6, dividing by 6, we are getting 0 as the remainder. Then 4 plus 4, it is 8, then dividing 8 by 6, 2 is the remainder. So therefore these are the elements of the addition modulo 6 table. So 0, 2, 4, 2, 4, 0, 4, 0, 2 means all the elements of this table belongs to H2, hence closure law satisfied. And again similarly 0, 2, 4 are the elements of G, and G is associative means H2 is also associative. And here the first row 0, 2, 4 is same as the topmost row, and the corresponding element is 0, and 0 is the identity element. Then here in the first row 0 is located here, then the corresponding elements are 0, 0, so inverse of 0 is 0. In the second row 0 is existing here, corresponding elements are 2 and 4, so inverse of 2 is 4, or inverse of 4 is 2. So therefore all the 4 laws satisfied for H2, hence H2 is a subgroup of G. H2 is subgroup of G. Now let us consider the results of the theorem. So in the first result, what we have? The intersection of two subgroups is also a subgroup. Now consider H1 intersection H2. So here H1 is 0, 3 and H2 is 0, 2, 4. So what is the common element here? So 0 is the common element, any group, and here 0 is nothing but the identity element of G, right? Because here for the group G, addition modulo 6 means that is nothing but addition only. So therefore whenever the binary operation is addition, then 0 will be the identity element. So therefore 0 is nothing but the identity element of G. Then we know that any group or any set having the identity element alone is always a group. So therefore it implies that H1 intersection H2 is a group because it is having only the identity element. There is no other element except 0. So therefore H1 intersection H2 is a group. If it is a group, then H1 intersection H2 is a subgroup of G. So it is for the first statement. And now let us consider the union of them, that is H1 union H2. So what is the union of these two sets, that H1 and H2? So that is 0, 2, 3, 4. 0, 2, 3, 4. Now let us write the addition modulo 6 table, because here it was only 0, then we have written directly that is a group, but here we cannot write like that. So therefore we need to construct the table for that given binary operation, that is addition modulo 6. So it is 0, 2, 3, 4, here also 0, 2, 3, 4. Again same 0 plus 0, 0, 0 plus 2, 2, and here it is 3, 4. And then 2 plus 0, that is equal to 2, 2 plus 2, 4, 2 plus 3, 2 plus 3 is equal to 5, then 2 plus 4, that is 6, then remainder is 0. Then here 3 plus 0, 3, 3 plus 2, 5, 3 plus 3, 6, and the remainder is 0. 3 plus 4, 7, remainder is 1, and 4 plus 0, 4, 4 plus 2, 6, dividing by 6, we are getting the remainder 0. Then 4 plus 3, 7, and the remainder is 1. 4 plus 4, 8, the remainder is 2. Now here, so this is the table for addition modulo 6. Now look at the elements of this table. So here we have only 0, 2, 3 and 4 in the H1 union H2. But here in the first row all the elements belongs to H1 union H2, and in the second row here we have 5, right? So this 5 is not belong to 0, 2, 3, 4 or H1 union H2. Then here also 5 and 1. So these two elements does not belong to the given set. Here also 1. This one does not belong to H1 union H2. So the first property only failed. What is the first property? If all the elements of the table belong to the given set, then we can say that the closure law verified for that. But here these elements are not belong to the given set, so therefore closure not satisfied. If closure law not satisfied, then we can not move further, because the first law only failed. If any one law of the 4 laws failed, then we can say that it is not a group. So therefore here only we can write the conclusion. Therefore here 5, 1 does not belong to H1 union H2. It implies that closure law failed. Not only closure law, if any law failed among the 4 laws, then it is not the group. So therefore H1 union H2 is not a group. So it implies H1 union H2 is not a subgroup of G. So therefore always intersection of two subgroups is a subgroup, but we cannot say that the union of two subgroups is always a subgroup. Sometimes it may happen, it may be a subgroup or it may not be a subgroup. So therefore this is the example to verify these two statements.